So good evening, everyone. As you may already know, my name is Sofia Fernandes, and today I'll be the one responsible for the public talk. I have decided to talk about how we'll be able to watch the universe expand in real time with the aid of forthcoming facilities in the next few years. This will be possible because of the redshift drift. The redshift, as the name suggests, is when the light of a cosmological object shifts in codes towards the red end of a spectrum. So it's a phenomenon that occurs in distant objects as a result of the expansion of the universe. With time, the redshift changes, which we call the redshift drift. Analyzing the redshift drift is a model-independent method to study the universe, as the majority currently needs to impose conditions in the constitution of it, therefore choose one of the existing models and assume it is indeed the correct one. In addition, the forecasts up until now do not consider curvature quantitatively. So there's numerous constraints sometimes required to be able to make advances in this field. Nevertheless, I'll be using a probe assembled by Mariana Souza, Professor Carlos Martins, and Catarina Martins, called Impacts of Curvature on Forthcoming Redshift Drift Measurements, which I have collaborated in my internship at CAUP and has not yet been published. This will be the basis of this presentation in an effort to shed some light to this matter. Note that even in principle, the redshift drift is model independent. We will be using it to place constraints on relevant models and their perimeters. As I previously mentioned, there are currently two facilities under construction that will be able to detect this phenomenon, which is ELT actually, that you probably remember the name as it stands for Extremely Large Telescope. It will be able to detect high redshifts, while SCA will be able to detect low redshifts. This way you can say that they will complement each other. So first of all, I want to do a type of introduction to the kind of tests you'll be seeing throughout the presentation, and they were thoroughly investigated throughout the probe. We'll start with the standard redshift drift, which has been thoroughly investigated too, but with little emphasis or not at all on curvature. And then we'll talk about the differential redshift drifts, initially in a conceptual manner, and afterwards for ELT observations, because it's not possible for SCA. So you have been seeing during my introduction these equations, which have been used in the plots and in the tables that I will see up next. But before that, we're going to talk about the sensitivity coefficients. The measureless redshift drifts, one is SV, and spectroscopic velocity one, SV. All right, we'll be using three models, which are omega k equals 0, omega k equals minus 0.1, and omega k equals 0.1. When I refer to omega k, I'm talking about curvature. So when I say that omega k equals 0, I'm talking about flat universes. That'll be the solid line on the next plot, all right? Minus 0.1 closed universes, the dashed line on the plot, and 0.1 dotted, open universes, and will be the dotted line on the next plot. On the other hand, we have the Hubble perimeter, H, which will be equal to 0.7, omega m, the matter density, which will be equal to 0.3, and WO, the dark energy equation of state will be equal to -1. These parameters will almost stay the same throughout your presentation. So now, in this figure, we see the sensitivity. So like we have the dimensional redshift here and the spectroscopic velocity here. We have realized that for closed universes, we have a larger sensitivity to all perimeters rather than in open universes. And in terms of dimensional redshift drift, omega k has a very, you see this line? Omega k is a very similar behavior to omega m, the blue line. But omega m has a larger sensitivity than omega k. Nonetheless, on spectroscopic velocity, omega k is a more similar behavior to that of WO. But this time, omega k has a larger sensitivity. If you notice, omega k and WO have like a maximum. You're at a low redshift, z approximately 1. So WO is the cyan line, while the omega k, the red line, is the same. And here we have an attempt to establish overall sensitivity. So what do? We have two cases where we get the absolute values of all perimeters and add them, and one where you get the set values, but we multiply them, which entails giving equal weight to determination of the model's perimeters. So blue and cyan will be sensitivity for the spectroscopic velocity, and red and magenta sensitivity for the redshift drift. This will be the addition case, while this the multiplication case. We also realize that at lower redshifts, we have larger sensitivities than in closed universes rather than open ones. But at higher, in open universes, we have a larger sensitivity rather than in the closed universes. Nonetheless, for the spectroscopic velocity, it's also viable to study the sensitivity at z approximately 1. Okay, so to conclude, we can expect that SCA will have bigger, let's say, no. The uncertainties of the spectroscopic velocity will increase as the redshift gets higher. It's not that hard to imagine since the sources are also scarcer. But this makes a problem for ELT because the higher redshifts enable something called Lyman alpha force, which is essential for ELT observations. So now we are going to use a Fisher matrix predicode to be able to add curvature to the plots and see the impact that it has quantitatively. All right. We have chosen 10 measurements. For SCA, they will be uniformly spaced. The redshifts will be between between 0.1 and 1. While the spectroscopic velocity will be also uniformly spaced between 1% and 10%. As for ELT, it's a different case. We'll be using the recently proposed golden sample. All right. Here we have the first plot we're going to see is in a 3D perimeter space. So we'll be only using H, omega m, and WO. So it's a flat universe. We're not using omega k. the values, as you can see here, are the same, and we are going to have the priors. For H, we have 0.1, omega M 0.05, and WO 0.15. So here we have the results of the code. You can see in the blue circle that we have better constraints for omega M and WO, but not for H, which is not surprising because H, the Hubble perimeter, is a multiplicative factor to the equation. So we don't have a good constraints of it. Not, we can do, you can have it, but they're not usually the best. And here, it's not going to be used immediately, but I'd like you for all to try to memorize a little bit of the values in the yellow rectangle, but don't worry, I'll explain later. So just keep in mind, we have better constraints than the assumed priors here in the pink circle, except for H. Now, we are still working with the flat universe, but we have something different. We'll be working with a 4D perimeter space. So we are adding omega k, but it's still 0. We'll be having the prior 0.2, which will make a difference, as you can see here. So we have worse constraints. You can see like the values are bigger than the assumed priors, except for WO. You can actually say that it could be like a good constraint on WO. But I want you to pay good attention to the yellow rectangle. You might not remember properly, but these values are way bigger. So so we have weaker constraints compared to the previous table. So when we didn't have curvature, right? And if you look at the black one, it's really worse than before for omega m. So like, for example, in the first we had 0.009, and here we have 0.037, correct? And you have something new, which is not surprising to you, but it's the anti-correlation between omega m and omega k. So you can see here, it's almost in all cases it's -1. Now we're seriously talking, we're seriously working with curvature. So we'll be using omega k with the value for closed universes, -0.1, and open universes are 0.1. But you can see the other values say the same. So this time we will compare it to table 2, the flat universe, and we'll have the other tables here. We noticed that omega k, the curvature doesn't impact as significantly as someone could expect, particularly with ELT, this column here. Nonetheless, we do have better WO constraints at closed universes. Yeah. The other changes are pretty unsubstantial to the perimeters. The significant difference is actually changing between the models, flat, open, and closed. And another important thing is these green ellipses. If you pay close attention to the difference between open and closed universe, you see what these figures and merits are almost double of these ones, except for the LT plus priors. Right, so we could say you have better constraints at open universes than closed universes. Now we are almost over with the standard redshift trait, and we'll start talking about the differential redshift trait. The differential redshift trait consists in comparing two different redshift traits of two different astrophysical sources in the same line of sight. Yeah. So we'll start, like I said before, the conceptual manner, and then we'll see for ELT observation, since scar's limitation at higher redshifts. We need to have two redshifts like ZR and ZI. We'll be using a ratio, ZY divided by ZR in the y-axis and ZR in the x-axis. We are trying to plot the behavior of the differential redshift drift. And keep in mind that ZI is smaller than ZR. So we could say that ZR is a high redshift while ZI is a low redshift. Logically, if the ratio comes to 0, we are looking at the behavior of the standard redshift drift, all right? We'll be also using the three models mentioned previously. Now we are kind of repeating the process we did before, but of course for the differential redshift drift. So here we have the sensitivities. Yeah, correct. And actually, we find the same results as the standard redshift drift. So for the sensitivity of the differential redshift drift, omega k has a similar behavior to that of the omega m, right? While for the corresponding spectroscopic velocity, omega k has a similar behavior to that of WO. Of course, you also try to establish the overall sensitivity. So we have the addition case here, and here the multiplication case. Omega k does provoke some substantial changes in the addition case. And multiplication case, we have higher sensitivity at lower redshifts rather than at higher redshifts. It's also important to say that the wider the range, I mean the ratio, we have the ideal scenario to do this kind of measurements. And well, we have the best results for both cases. Nonetheless, we do have good constraints on WO and omega m. Now we'll be joining, let's say joining the two redshifts. So it might not be obvious, but for the differential redshift drift, there's no data sets, there's no measurements about the differential redshift drift. So we'll have to assume that for each target the ELT we'll be using 7. We have an extra measurement for the differential redshift drift. We'll assume they all have the same ratio, which will be between 0.15 and 0.85. And we will assume that the spectroscopic velocity will be proportional to that of the standard one. And you have 3 cases for that. So the velocity uncertainty, the spectroscopic velocity uncertainty could be the same as the standard one, which is ideal, but not likely. And the worst cases and they're more likely are that the velocity, the spectroscopic velocity uncertainty of the differential redshift drift is 2 times worse than to that standard, and the third case is that it's 4 times worse. Of course, we'll also be using the same models as before. So now is the last table for today. You can see we have the priors here only, then we have only the standard drift, and then we have them together. It's important to understand that we have 3 perimeter space here, so 2D, 3D, and 4D. 4D, of course, it's with curvature. 3D doesn't have curvature. And 2D, it's a flat lambda CDM model. So when we have joint measurements, we have the best result when the spectroscopic velocity uncertainties are the same. In 4D, the figures and merits improve by 40% than the assumed priors for the standard drift, the redshift drift. But if we add the differential redshift drift, it only increases 15%, I mean. Well, which is which is a little bit lower, of course. And it's only if you use a larger ratio. Oh, we also realize that the sensitivity is larger to enclosed universes rather than open. And now this will be our last figure. So this represents the gains afforded by the differential redshift drift measurements, depending on the ratio and the spectroscopic velocity. We rescale the figure of merit to priors only, and the behavior turned out always the same. But in this case, so we have a large impact at low ratios, and the sensitivity is substantial when velocities and spectroscopic velocities and uncertainties are equal. In fact, if you notice, a factor of 2 moves almost the gain. So here we have when the velocity uncertainty, the spectroscopic velocity and uncertainty are equal. Here by a factor of 2, by a factor of 4. Right. So, in conclusion, I have tried today to show you how researchers' work, my work, and researchers' work functions, let's say, how they try to understand the universe, and particularly how I started my journey on this field. You got access to a simple assessment of the sensitivity and cosmological impact of SCA and DLT, especially with a novelty such as the differential redshift drift, and you got to see the experiments with the open and closed universes. In short, you made some discoveries today, I believe, and which the main points are this. Well, the sensitivity is larger for closed universes rather than open, and that behavior of omega k when it has a similar behavior to omega m when in terms of dimensional spectroscopic velocity, dimensional redshift drift, and a similar behavior, but omega k is a similar behavior to that of WO in terms of spectroscopic velocity. Besides that, you also got an assessment of joint measurements of standard redshift drift and, well, the differential redshift drift. We have concluded that comparable sensitivities into intervening redshifts between 0.75 and 1.25 allow the ideal scenario for this kind of measurements. Anyway, it's plausible to say that with ELT especially, we'll be able to study both the standard redshift drift and differential redshift drifts.